So last time I gave you all three different definitions of UFD. I really didn't justify at all that they were connected. It was quite clear that the second one implied the third, but it wasn't clear at all that the first one implied the second. Well, I'm going to start to tie two of these together, at least. Let me give you the following proposition. And this is, to me, this proposition is something that really separates prime from irreducibles. Let R be a domain and X in R. So X is some of the domain. If X can be written as a product of non-zero primes, so I want, of course, X to be non-zero, and I'm in a domain, so I don't have to worry about things multiplying together to get zero. If they're not zero, then this representation is unique up to ordering and associates. This term here, I may have used in passing for two elements are associate in a domain if they vary by a unit. So let me kind of write this down. X and Y are associates if X equals UY for some U in the unit star. So this was a big, because what it says is whenever you find something that can be written as a product of primes, that's the only way to write it. Any other factorization into irreducibles will be that factorization into primes, perhaps permuted with some associates. So let's see why this is true. We proceed by induction on number of prime factors. Certainly, if it's only got one factor, this works. That is, then this is the only way to do it, because we know that a non-zero prime is irreducible from earlier. So this is the only way to factor this up to associates, right? So now suppose a statement holds if X is a product of M primes for any M less than or equal to M. Right, so all the strong induction thing. And now assume that we have, so if I have any product of primes that has N factors or less, then the statement holds. So now let X equal P1, P2, Pn. Now suppose it's a product of N plus one. So we want to show that this is the only way to do this. Note that Notice that my newest prime, Pn plus 1 divides x. That's what I want to do. I want to show, of course, that this is the only way to do this up to associates. So let's try this. Now suppose that x factors this way, which with each of these factors irreducible. Now, of course, what you have is note that so we'll say that P n plus 1 divides m without loss of term. Because of course Pn plus 1 divides this product, but it's prime, which is super strong, which means it's got to divide one of these irreducibles. We will say that it divides this one, the last one, Pm without loss of generality. This means, of course, that pi m is Pn plus 1 times some, let's say R, some R and R. And what do we know about R? It must be a unit, right? Because pi m is an irreducible. So R is in the units of R as pi m is irreducible. Hence, pi m is prime, as a matter of fact, because it is a unit multiple of prime. Yes.
Why did we not just say, let x also factor is that with each by prime? Because the statement of the theorem was that.
Yeah, but see, I'm showing that any irreducible factorization is prime factorization. Right. So in fact, I'm doing something stronger here by assuming these are just irreducible. Right. And in fact, here's kind of a purple bit of a linchpin right here, because we've discovered along the way that whichever irreducible this thing divides must in fact be prime. Right. Notice that this means that this I n 2 n minus 1, and then pi m is p n. That, right, where let me remind you, and now I'm kind of regretting that I didn't call this, where this part of the proof R is in fact a unit, right? And of course, this is a domain, so we can cancel. So now we get pi 1, pi 2, pi m minus 1 times a unit is equal to P1, P2, Pn. So by induction, m minus one is equal to n, because the uniqueness by induction we have, and each I is associated with some Ej, right? And so that essentially does it right there. Because this is unique. This factorization here is unique because you've got your Pn plus ones, and by induction, you've not got the rest. Any questions on that? So let me make an observation. So this is a very important theorem because it shows that in any domain, whether even if you're not even atomic, if you happen to have an element sitting in there that can be written as a product of primes, then it factors. That's the only way to factor it, in fact, into irreducibles at all. Right. So proposition 7. And this is a small observation here, but it'll be useful later. Let R be the domain, and S and R the subset of elements written as they can be written expressed as a product of primes or units. Let me explain what I mean by this here. So a typical element of S so it's basically the set of everything that you could write as a unit times a product of primes, and that product of primes could be empty, right? It'd just be a unit by itself. Then S is multiplicably closed and saturated. Right, so look at the forms of the elements, right? The product of two units is a unit, checkamundo. The product of a product of primes and another product of primes is a perhaps larger product of prime. And a product of primes times a unit, the unit can be absorbed in any one of these primes and still a prime, right? But okay then. So multiplicative closed is easier. Why is it saturated? Well, to see S saturated, suppose AB is an R and AB S. Let's see how sloppy I can be on this one. What does it mean for AB being S? Well, let me point out that if AB is a unit, then A and B are units. Because if, for example, ABX is 1, this means A times BX is 1, which makes A a unit, and if B times AX is 1, makes A a unit. So no problem there. The only thing we have to worry about is if AB is a product of primes. So suppose AB is P1 P2. Okay. So how do we proceed from here? Any ideas?
You got your primes on the right, then kind of divide.
That's right, that's right. So, if you divide, notice that P1 divides AB. So P1 divides A, or P1 divides B, right? So pick one, right? So now what you have is, let me make a statement here. So suppose P1 divides A, and hence, A equals P1, A1. So now what we have is we have A1, B is equal to P2 up to PK. Right? Now, we continue this process. Now P2 divides either A1 or B, and you keep going. And so continuing this process, eventually we get AJ BI is equal to 1. Where J, the P's divide A, and I of P's divide B. And in fact, we can, so what this means is that, well, what does this equation mean about AJ and, or A sub J and B I? Means they are both units, right? So AJ, a unit. And how did we come from AJ? Well, we got AJ by dividing A by some J number of these P's. So what this means is A is equal to AJ times P T1, P T2, P TJ. Where these are the appropriate subscripts of the original that divide this. So in particular, A and S, because it's a unit of the product of primes, right? And of course, symmetrically B is as well. Okay, any questions on that? I'm going to make one more little kind of small observation. So now what we have is we have the set of elements that can be expressed as it's either a unit or it can be expressed as a product of primes, must be multiplicatively closed and saturated. By the way, do you smell what the rock's cooking? What do you think is coming up with this business about the set of properties close and saturated?
Well, something to
That's right. We know that, so in particular, this set of elements that can be expressed, it's either a unit or a product of primes, must be the complement of union of prime ideas, right? So that's what's coming. Let me make a small observation here. And that is, an integral domain if R is a domain, R is a UFD. If and only if every non-zero non-unit is a product. I really dig on that, right? Because the original definition of UFD, it involves all this kind of business. It involves, okay, the thing's atomic. And now if you've got two irreducible factorizations, the links have to be the same, and now you can pair them off. Here, you don't even have to say atomic, right? If you're an integral domain, all you have to be able to say is everything that's not zero, not a unit, can be written as a product of primes. That gives you atomicity in the definition, strongly gives you atomicity. And from our earlier result, we know that product of prime, things that can factor with product of primes do so essentially uniquely. Right? So this gives us everything we need. Right? So here is the fancy characterization that I had promised. And not only is it fancy, so we can go home and feel really good about ourselves for knowing this, it actually also shortcuts a lot of classical things. There are theorems that you've seen. Principal ideal domain implies UFD. It's annoying, it's obnoxious, and it requires choice. Going this route, we sort of do the heavy lifting earlier in going this route, and this kind of more streamlined way that I'm going to show you gets that result. Also, here's another great UFD result. If you have a UFD, it's polynomial rings UFD, right? This result makes this easier as well. And so without further ado, theorem uh, 149. The following conditions. One, R is a UF. That is every non-zero non-unit, or right, can be written as product of primes. Two, every non-zero prime ideal. Of R contains a non-zero principal prime ideal. Now, let me give you an example, and then we'll talk about the proof of this. What this means is, so let's think about what this means here. If you have a ring and you've got some prime ideal, and my only requirement on this prime ideal is to stop the zero. Zero is a prime ideal in this ring, but we got to toss that out the window. What this means is there is a perhaps smaller principal prime generated by some little p in here. Notice, be careful. I'm not saying that this prime is generated by this. This might be a much smaller ideal. So, for example, depending, the nature of the prime ideal can vary depending on what the field is. All right. So, for example, the ideal x squared plus 1 the ideal generated by x squared plus one is prime ideal in this range if f is, say, the rational numbers. But it's not prime if it's the complex numbers, because the x squared plus one breaks down, right? But let me give you, for example, a prime ideal. In fact, this one's a maximum ideal. This one contains what we would unofficially call a boatload of principal prime ideals. Right? There's lots of them in here. The ideal generated by X. Right? That's certainly not the whole thing, but there's a principal prime there. The ideal generated by Y. Right? The ideal generated by X to the 27th, Y to the 9. Okay. Plus Z. By the way, how do I know that this ideal is prime? Right? These seem pretty clear when you mod out by this. You get. What about this one?
I want to see GCP something without further.
Yeah, this might be the right prime.
Eisenstein criteria, can we use that?
Okay, but if you're gonna use Eisenstein, what's your polynomial?
Yeah.
Right, so I think your idea is right? So it looks to me like Adam is doing this. And I think that's a good way to think about this. This is degree 1 in Z. So if you think of this as a polynomial, the coefficients are x, y, and this is Z, this is degree 1 in Z. How you gonna factor it? Right? It has to break down into something of degree 1 and something of degree 0, and that's where you run into problems, right? So anyway, the point is this thing contains a whole bunch of these. This is a terribly important theorem, so let's verify this. Oh, actually, let me give you a ripoff. I love ripoffs. Corollary. How many of you all have all seen theorem? Any principal ideal domain is UFD, right? Converse doesn't hold true in general, does it? Corollary. R is a PID. If and only R is a unit. And dimension is less than 1. So this is a characterization. PIDs or UFDs where the Kroll dimension is no bigger than 1. Now, I haven't told you what the Kroll dimension is yet, but let me put this in simple terms just for right now. This means dimension R equals 1 means every non-zero prime ideal is maximum. Basically, what the dimension measures in a range, we'll get to this later, is how high you can stack your prime ideals. This means every non-zero prime ideal is maximum. Right? Dimensions R equals 0. Let me say in domains. Dimension R equals 0 means R is a field. Because essentially, and again, we'll get to this later, essentially what dimension 0 means for an integral domain is it means that 0 is a maximal ideal, right? So this is kind of neat because, you know, I remember the first time I ever saw PID implies UFD, it seems like there's a missing puzzle. It seems like these were kind of close, and here's exactly what you need. PIDs are precisely the small UFDs. Right? Let's use this theorem to prove this, because this is a nifty result. truth of the corollary. If R is PID, then R is a UFD. So there's one piece of puzzle. Now we have to do this dimension business. Well, if R is a PID, if R is a field, then that's obviously holes. So let's assume that R is a PID, it's not a field. Let M be a deal. And in my file. Okay, suppose we have a PID. I want to show that every non-zero prime ideal is maximal. So let's assume that R is not a field. And let's assume that we've got some non-zero prime ideal here. Well, of course, my prime ideal must live in a maximal ideal. And our burden is, of course, to show that these two are the same. And this is factorization techniques. So any ideas on how we might show that P and M are the same thing?
They're both principal prime ideals.
Okay, and that right there, I mean, that's the death knell right there. Since R is id, then P is contained in M. Let's say it's generated by X. Well, how about let's make that a thing. We know since P is prime, so is little p, right? Because that's one of the characterizations of prime elements that generates a prime ideal. And since the ideal generated by X contains the ideal generated by P, this implies that X divides P. Right? Because it must divide that because P is in this ideal. Therefore, P is Rx for some R, and R is it has to be a unit because P being a non-zero prime is irreducible. But that means that P and X are associates. And the ideal generated by P is equal to the ideal generated by X. So we've got that. A non-zero prime is max and a PI. Okay. Now what about the next one, right? The interesting, as you might guess, the interesting application is the other way. Every non-zero prime ideal contains a non-zero principal prime ideal. We want to show that it's a PID. So for the other direction, we claim that, what do we claim? Every So first I'm going to make the following claim. I claim that every prime ideal for this direction here, I claim that every prime ideal of R is principal. Well, let And let's suppose that my prime ideal is not zero, because otherwise it's kind of silly. Right? So what do I know? I know that every, well, so I know that R is a UFD and the dimension is less than one. Since R is a UFD, there exists a prime element, a non-zero prime element X and R. So we have 0, we have the 0 is, of course, a prime ideal, the UFD. This is contained in X. Did I miss something?
Are you grouping? Oh, yeah.
I'm trying to show that, this corollary, that R is a UFD and the dimension of R is less than or equal to 1 means that it's a PID.
Your P has extra legs.
What's that?
Your P has an extra leg there.
Exit.
Should be a P.
Non-zero prime element X.
Oh, is this the extra leg here?
Yeah.
Okay, yeah, well, let's perform a little amputation there.
Yeah.
There we go. Are we good now? Okay. There exists a non-zero prime element X and P, such that we have this here. 0 is strictly contained in the ideal term by X, which is contained in P. And in fact, since R is a PID and X is prime, that's sort of PID. Since R is dimension 1, because we've already said that it's not a field, and this is prime, this is maximum. Because it's a non-zero prime ideal, so it's maximum. Therefore, so our conclusion is conclusion every prime ideal of R is a is present. Hence, every ideal of R is present. And I will give this on your next exercise set. This is kind of a fun thing. I'm going to do something similar for Noetherian in a minute. It's also true. This is one of the reasons why principal ideal domain is again kind of a good ring theoretic property, because it's determined by primes, right? If you have a principal ideal domain, it's clear that every prime ideal is principal, because every ideal is principal. However, that's all you need. If you have a domain where every prime ideal is principal, then every ideal has to be principal. Right? So this is an exercise. This proof is incomplete, but it segues into one of the things we're going to do on the next exercise set. Let's prove the theorem itself. So we want to establish this theorem because it's an amazing theorem. Proof of 149. One implies two is the easier part. So really, to show one implies two, we have to show that every non-zero prime ideal contains a non-zero prime element. Agreed? What do I know about a non-zero prime ideal? Well, what do I know about a non-zero ideal? It contains a non-zero element. So there exists Z equal not zero such that Z. Now, any UFD, what can I do to any Z that I encounter? I can factor it, in fact, into a product of primes. So these are prime factors. And of course, Z is NP. And what do we know when we have a product of crap that's in prime ideal? One of those things has to be in there. Without loss of generality, say P1 is in P, and there you go. There's your non-zero. So that wasn't too harsh. And of course, I guess it's no surprise that the other direction is the interesting one. Why is it true that all you have to do is require every prime ideal to contain every non-zero prime ideal to contain a non-zero prime element. That's good enough to get unique factorization. So let's look at that. Suppose every non-zero prime ideal contains a non-zero prime element. We want to show that it's UFD. So the first thing I'm going to do is I am going to pick out a multiplicative set. Let S equal the set of X and R such that X is a unit for the product of primes. This is the set we dealt with earlier today in class, right? What do you suppose my goal is with regard to S? Yes, I want to show it suffices to show S is everything in R except for zero, right? Because if it's a UFD, remember, to be a UFD, all you need is every non-zero non-unit is a product of primes. Well, so what this means is your non-zero elements are either a unit or a product of prime. So if S and R minus zero coincide, then we're good to go. Let's suppose not. So there's a non-zero X and R that is not a unit or a product of primes. Now, what I want to do is I want to look at the ideal generated by this. I'll consider the ideal generated by this element that is not a unit, not a product of primes. What do you think is true about this? That's right. This has to be the empty. Can somebody explain why?
I earlier there.
That's exactly right. That's exactly
Kind
right.
of like an arbitrary
I
answer.
just
You know exactly what
That
I
was
mean.
kind of a clever answer on your part, right? But yes.
You know I what I mean.
If Rx equals S,
Some of the previous days.
then Rx is a product of primes. Which is a saturated set. Actually, it's multiply. It's multiply close and saturated. Remember how we showed that the set S, that's either units or product prime, is saturated. Now, if Rx is in S, then it picks up all the divisors, which implies that X is in S, which is a contradiction, because X itself was neither a unit nor was a product prime. Yes.
Couldn't we streamline this after you assume, so it suffices to show that its complement is just a zero? So assume not, and then can we just use saturated to say the complement is non-empty and it's a union of prime ideals, because it's saturated?
Yeah,
You automatically get a prime ideal that has no primes in it and you're done.
That's where you're right, that's probably quicker. I'm gonna get to that road this way as well, but it's equivalent to what you're saying, so you're absolutely right. So everybody good with me here? So this intersection has to be empty, right? And so that means so we can expand X to P of X. Such that P of X is prime and maximal with respect to P of X intersect as empty. And there's your contradiction. So PX is a prime ideal containing no is a non-zero prime ideal, containing no non-zero prime elements. Because of course, all the prime elements that are non-zero have to put an S. Right. But yeah, what you were saying, Jared, that's really the same thing. Okay, I am going to give you, just time for one last theorem, which I won't prove, probably for kind of obvious reasons, because one way or another, you probably have to show this on in your homework. Proposition, this is propositions definition, so I kind of introduced the notion in here. Let R be a commutative ring of identity. The following conditions are equivalent. Number one, actually, I'm going to put this all together. Every ascending chain of ideals stabilizes. That is, there exists in the natural numbers such that IM equals IM plus 1 for all M bigger than or equal to N. So this is like ACCP, except I don't demand that these ideals all be principal. Number two, every ideal of R is finitely generated. And number three, every prime ID R is finitely generated. Anybody know what we call a ring that satisfies one and hits all of these equivalent conditions? Yeah, this is, these such things are called theorems. And this is the one that you may not have seen before, because again, to take the PID thing, the theorem suffices only for the prime ideals. If the prime ideals are finitely generated, then all the ideals. That's one of the things that where you know you've got a good property when it holds, when it's good enough to check on the primes. Okay, any questions? All right, well, I will see you all on Friday. Oh, the math club might be fun. It's probably nothing you all don't already know, but I'm gonna talk about infinite sets and counting, so. Hopefully it'll be kind of fun.